Excellent connection.
Seems to be very delayed because it showed me walking across. Oh, there you go. Oh my gosh, there's another cannon.
Yeah, you go.
Okay.
It's a touchscreen on Jason.
Or no, you probably moved on from UTE by the time you should have thought ahead for 5 hours. Shortly after.
Okay, little seal, I know you're there. Please get me in.
I am objective, but I will buy all the until I get back. That would have been like 2000. No, 2005. I moved here in 08.
Whoops.
Where'd you come from?
Oh.
Is it bad?
Enjoy the infinite screen. How do I?
Laptop doesn't work?
It's just not good. Oh, it's just not connecting to the HDMI. Right. Okay. Yes. Indeed. Cool. Is it? Okay.
Did it show?
Let me get to where I was going to go.
Extrapolation is exactly what it is.
Okay, computer. How about you load anything?
It was really sharp. He's doing great.
Okay. There we go. That looks good.
Yeah, he's great. It's also a word that is very relevant for video game. Yeah, it's busy enough, and with like non-disclosures, it's hard. It's kind of hard. We do work mostly on the commercial side, so yeah, it's a lot of selling, image processing, and extracting 3D models.
That's a great idea.
Relatively speaking, it's better than somebody else working on.
A what?
Like a drawing pen.
I don't know how that would
You can like click the skill button on it. That language.
Yeah.
If the mouse is sort of.
Yeah, I can't think about everything.
I don't know. I think this will probably work.
Okay.
That's gonna like create a tripping hazard.
You have power here.
Oh, I do? Okay. Cool, because yeah, I'm not super. Okay, yeah, that makes sense.
Does he work, which facility within Rippentrop do you work at?
Alrighty.
Okay.
Alrighty, yeah.
Well, hi, everybody.
What's his name? I definitely need to clean up the fridge.
Good evening, everybody. Welcome tonight. We've had like 3 weeks in a row of weird weather stuff keeping people away, but thank you all for being here. Let's see, we're going to go to Cain's tonight after this, and on Saturday we are going to watch a debate with William Lane Craig about the existence of God. I'm pretty sure all of you were in here when we were talking about this, so I don't need to announce this to y'all. But hope you all be there in our normal room at 7. Anybody who's watching online will be aware of that as well. So that we'll be ready for having him join us on Zoom in a couple weeks, which will be very interesting. But even more interesting now is Seth, who's going to be talking with us about fine-tuning.
Alrighty. So, yep, I am going to be talking about fine-tuning tonight. In case anyone doesn't know, I'm Seth Rippentrop. I'm a first semester physics PhD student here at UTD, but I did my undergrad here as well. I work in cosmology. I do research in cosmology. And so definitely a lot of overlap with fine-tuning, and definitely a lot of where I'm going to take some of this talk definitely goes into some cosmology because I just couldn't help myself. But, so, anyway, let's go ahead and jump right in. So, to talk about fine-tuning, we really need to talk, and we need to start with fundamental constants, understanding these. So, in physics, there are certain physical laws that, can be derived from mathematics. We can formulate these laws and relations through just, math alone. We can have certain mathematical equations that lead to other ones that lead to other ones, and a lot of this is derivable. Like, we can figure this stuff out just through pen and paper. We can get different laws through math. The problem is riddled throughout a lot of these laws, pretty much all of them. There's these things called fundamental constants. And consider gravity. This whole equation is classic if you've been in any kind of physics class. It's the equation, the force equation for gravity. For the gravitational force is equal to g times m1, m2, r squared. And so, you see here that like we have m1, we have m2. These make sense. Larger masses, more gravitational force. We can switch them if we want, and it's going to be the same equation, which makes sense. We can always just move the masses around. They're going to be the same scenario. R squareds are distance. Gravity is going to decay as we get farther away from the source. That's all good. The weird thing here, though, is that g. That g is just kind of a placeholder value. There's nothing in the problem that like we can get that g from. There's no math we can do to like derive its value. It has to just be measured. And indeed, it was measured. Indeed, it was measured by that little what's going on, mate? Okay. Indeed, it was measured by the Cavendish experiment, which is that little weird little pendulum over there. Had kind of a mass on a wire, and subtle differences in the movement of those masses was able to determine the strength of that value. The point here is, though, we didn't find the value of g through math. We found it by measuring it. It could have been any value, and we just found that it just happens to be 6.67 times 10 to the minus 11. But it really could have been any other value. So keep that in mind. Additionally, we also need to talk about initial conditions. Some physics, when one performs like an experiment or something, or makes physical prediction, there's going to be like an initial condition to it. Imagine, just throwing a ball on a trajectory. We know how that ball is going to like move. We know how it's going to act because it's going to start moving down because of gravity, but it's also going to be moving forward because we threw it with a certain velocity. That's just how it's going to move. So it's going to move on a parabolic arc if you do the math. Little hump like that. The problem is we don't really know, just from like gravity and stuff, you can't tell how that's going to be shaped. Is it going to go up and then straight down? Is it going to go really far? That's going to depend on how you throw it. Do you throw it up? Do you throw it far? Do you throw it hard or soft? These are initial conditions to that problem that you don't just get from physics. You have to like take into account what the person that's throwing that ball is actually doing, how that ball starts its trajectory. And so even the universe itself has initial conditions like these that we can't just know a priori. So, for example, matter was clumped in certain densities at the very beginning of the universe. These were very specific values that we can't really derive from any physics. We just have to measure them. And we'll get more into that later. So basically, the notion of fine-tuning is that these fundamental constants or initial conditions, and I'm going to be referring to them collectively as parameters for the rest of this talk. So just when I say parameters, no, I'm referring to both of them. But these parameters of the universe were, if they were slightly different than they currently are, life would be impossible. That's just the notion. Obviously, I've done nothing so far to back this up, but this is at least the claim. So if parameters like, for instance, gravity, cosmic expansion, universe density, the ratio of electromagnetism to the other forces, mass of quarks, lot of other things. If they were changed by imperceptible amounts, the universe just would not be recognizable. It would be completely different and very inhospitable for life. So let's try to explore this. The thing is, though, when we're thinking about this, we're kind of thinking about a possible universe. In that we're thinking these what-if scenarios. What if the universe was a bit different? What if this constant was a bit different than what we measured it? Because there's nothing locking that constant in place as what we measured it. What if it was a bit different? But when we do so, we're looking at a universe that is different from our own. So we can think of this as exploring many hypothetical universes where parameters are a bit different, and pondering, and better than pondering, doing the math to figure out what those universes would be like. And so in no way do these universes actually have to exist for us to think about this. I will get to this more later. But at this point, it's just a thought experiment. So let's go ahead and start with an example. And I know we've had quite a lot of fine-tuning talks in the past, so the main focus of this talk is not really as much on these examples, and it's not just going to be a bunch of, oh, this is tuned to 1 part in 17 billion. Like, I'm more so just going to give kind of a qualitative approach to some of these examples, just to give you an idea of what fine-tuning is like. There's a lot of others that I'm not going to mention here. These are just ones that I found interesting and I don't think have been mentioned very much. So let's take an example from particle physics. So the atom is made of protons, neutrons, electrons. You know, they should be quite familiar to us. The thing is, electrons are fundamental. There's nothing smaller than them. There's nothing that's like, there's nothing that's making them up. Protons and neutrons, not so much. They're what are known as hadrons, which means that they're made of these smaller quarks. And quarks can come in a couple of different variants. Most common of these variants are up and down. 2 up quarks and 1 down quark is a proton, 2 down quarks and 1 up quark is a neutron. And this is what we're familiar with every day. The quarks, electrons, and some other ones make up a class of particles known as fundamental particles. These are the smallest basic building blocks of the universe. Yes?
Could you remind me how we know that quarks exist? I know that I've studied this, but I forgot.
Honestly, off the top of my head, I'm not sure if I can recall like what experiment proved that quarks exist.
Somebody figured it out. I was just curious.
Yeah, because like we can't technically like split a proton or a neutron. The more you pull on them, the harder they pull back. But yeah, I'm not entirely sure. It probably gets down into some real obscure stuff. No, it's all right. Maybe. Yeah, I was about to say, I'm sure they knew about it before the LHC. Well, I feel like. Well, to take that back, we found a lot of, and this is where I'm going with this, we found a lot of different kind of hadrons. Particle physicists in the 60s were actually really afraid of this particle zoo, they termed it, of, oh, we're getting so many different fundamental particles, the universe is just hopelessly complicated. It was later then they realized that, oh, well, if they're all made up of different numbers of quarks, then that simplifies the picture a lot. I'm sure there's more experimental evidence for that, but that's kind of the thought process they went through. But yeah. All right. So this is a list of the fundamental particles. This is known as the standard model, basically the periodic table of fundamental particles. So the thing about them is they're nice. They're very simple. Very simple in the fact that you can see the only 3 numbers on here are mass, charge, and spin. That's it. That's all we need to use to describe these things. They just have a mass, they have a charge, and they have a spin. If you'll notice, I know these numbers are small, but charge and spin are like really orderly fractions on here. It's like 2/3, minus 1/3, minus 1. Spin is 1/2, 1/2, 1/2. There's a 1 spin, 0 spin. These are all like very like normal numbers. I don't think we need to like stretch our brains too hard to think about how these numbers came about. And the ratios between them, like the muon has the same charge as an electron. The down quark has 1/3 of the charge of an electron. Like they're all ratio values of each other. This is normal. The particle masses, though, are strange. Here we have 2.3. Here we have 1,275. Here we have 173,000. Here we have 4.8, 95, 4,180. These are very strange and random values. Now, you may say, oh, well, that's just because we didn't, these are just human units. Like, of course, they're not going to line up. And I agree. But the ratios between these numbers don't line up either. So when you divide, 95 versus 4.8, that's not going to come out to a nice round number. And the ratio here isn't the same. The ratio here is not the same. The ratio here is not the same. Or even multiple values of each other. They seem completely random. We have absolutely no way to predict these masses. We can only measure them. And so the question arises, just like in the whole G case and gravity at the beginning of this, what if there were different values? You know, surely it's something worth pursuing, something worth thinking about. So let's say we change them. So like I said, only 2 quark combinations are really commonly found nowadays, the up-up, down, which is proton, and the up-down-down, which is the neutron. So the protons are the most stable. Neutrons can only be stable in atoms. They kind of just fall apart if you take them out of atoms. But there's other hadrons that exist. For instance, the delta++ hadron is too heavy. It's very unstable, but it's made up of 3 quarks. And a hadron is just something that's made up of quarks. But the delta++ is made of 3 up quarks. And there's other ones out there as well. So if we change the quark masses, we can change the stability of different particles, which can end up leading to some very different universes. So let's take a look at that. So if we increase the down quark mass by a factor of 70, and now you may look at that 70 and say, well, that's a pretty big number, like 70 times the current quark mass to get something to happen. And, you know, perhaps that's a bit fair, but some of those ratios that we were looking at earlier, like the ratio of the top to the up quark, is somewhere around 75,000 maybe, maybe even 100,000. And so compared to that, 70 doesn't seem all that big. Like the quark masses cover a huge range already, just in their current values. That's not even to say that they could go higher. So even if we multiply the down quark's mass by 70, it's actually still pretty small compared to how big quarks can get. But let's just say we do this. Only helium exists. That's it. That is the universe. Helium. Nothing else. Technically, it's not quite normal helium. It's a little bit of a variant of helium, but it acts like helium. The problem with this is helium's inert. If anyone remembers a bit from chemistry, helium is on, you know, like the right side of the periodic table. It's a noble gas. It doesn't react with anything. It has no molecules. So in this universe, there are no molecules. There are helium atoms bouncing around, doing nothing. And it's very hard to get anything complicated out of that. It's very hard to get anything out of that, much less anything remotely resembling life. If we increase the up quark by a factor of 130, only an alternative version of hydrogen would exist with the charges flipped. Basically, instead of having a positive nucleus and a negative electron going around, you have a negative nucleus and a positive positron going around. But same thing. In this case, we actually an improvement. We get a single molecule. Hydrogen and hydrogen can join together into dihydrogen. And they can, you know, assumedly also be broken back apart. That's chemistry. That is all the chemistry in that universe. 2 atoms join together and they break apart. That is all chemical reactions. If we increase the down quark by mass of by a factor of 3, supposed to say factor there. So now we're getting smaller, just a factor of 3. No neutrons, only hydrogen again. So in this case, this is our normal hydrogen. We get our normal hydrogen back, a proton and an electron. But neutrons just don't exist. And again, we get 1 molecule. It's dihydrogen. And perhaps the most boring universe of all, if we increase the up quark mass by a factor of 6, all protons become neutrons. Protons just can't exist anymore. They all just become neutrons. And so that's only neutrons. So in this universe, atoms don't exist. Neutrons have no charge. They can't hold electrons to them. So they just float around in a neutron soup forever. That's the universe. And the same will occur if we decrease the mass of down quarks by 8%. Now we're getting to some quite small values, just 8%. And that's the kind of universe that awaits us. So another example can be from nuclear fusion. So briefly setting this up. Nuclear fusion is a way of generating energy from atomic reaction, like nuclear reactions. Now this is very different, not very, but this is a bit different than the kind of nuclear energy you're probably familiar with that we harness for power that's in nuclear power plants. That kind of nuclear energy is known as nuclear fission. This is taking very large atoms like uranium, plutonium, these things are huge, very unstable, and breaking them up into smaller atomic nuclei. And this generates a lot of energy. Thing is, though, when you go to the smallest atoms, when you split them apart, it actually doesn't generate energy. It takes energy. It takes a lot of energy to break them apart. It's really hard. But when you fuse them together, when you just smash two of them together and make them stick together, this generates a ton of energy. This is a process known as nuclear fusion. And it involves, yeah, basically just sticking different stuff in an atomic nucleus together to make new atoms. So here is a reaction where we have deuterium and tritium. These are isotopes of helium, just different kinds of, hydrogen. Different kinds of hydrogen joining together and creating a helium atom. And so we get heavier atoms out of lighter atoms. And so this produces a large amount of energy. Problem is, atomic nuclei are positive. They all have positive charge. Like they're made of protons and neutrons. That's positive charge and zero charge. So net charge is positive. So opposites attract, say like charges repel. Nuclei don't like to stay together. If you try to shove them next to each other, they're just going to repel away. The thing is, what helps to get them to actually stick is if we're moving them at really, really high speeds. If we shoot one at another one at an extremely high speed, they will finally stick together. The thing is, what is high speed for an atom? It's high temperature. Really, really high temperature. And also, atoms are really empty. And so to actually get a good chance of two atomic nuclei colliding, we need a very high density environment for this. What is a very, very hot, very, very high density environment? A core of a star. It's a perfect place for it. There is a ton of matter there in a very small volume, and it's so unimaginably hot. So nuclear fusion occurs a ton in stars all the time. A strange problem, though, arises when we consider the fusion of carbon. So carbon is very necessary for life. Just wanted to give a picture of a, DNA molecule here, made up, color-coded based on the atom. All the gray you see in there, that is all carbon. We are carbon-based life forms. We need this stuff. It is a very good molecule for chaining together into complex structures, which you need for life. Yeah. Yes. Yep. I basically bet a 90% chance that question would come up. While, it is theoretically possible, it is not nearly as optimized as carbon for forming complicated strands like this. Like it could, I wouldn't entirely rule out the possibility of it being simple life. I don't know a ton about it, but I would doubt silicon would be able to create life anywhere near as complex as what we see.
In fact, you have to go through carbon to make silicon.
That is true.
Stars.
That is true, yeah.
It doesn't really diminish fine-tuning much, even
That's true. That's true. I was going to kind of get there. The thing is with carbon is, like all of the elements, so including silicon, besides helium, hydrogen, and lithium, so all the elements besides those, the only way we can get carbon is if it's fused inside a star. The thing is, though, in order to produce carbon-12, we need 2 helium-4 atoms. They got to fuse together into beryllium-8. Then another helium-4 has got to join with beryllium-8, become carbon-12. 4 plus 4 is 8. 8 plus 4 is 12. Hopefully that makes sense. So this is all fine and dandy. Nice little process we can get together. If we get enough helium in one place, it's bound to happen eventually. The problem is beryllium-8 just doesn't like existing. It decays almost instantly. 10 to the minus 16 seconds is its lifetime. So the moment it's created, it just blips out of existence. And just becomes helium again. So that's a problem. So in order to get like a sufficient amount of beryllium, we need to get so much fusion happening and so much helium in one place that the beryllium just doesn't even have time to decay before it gets turned into carbon. But in order to do this, we need a star with a core temperature of 100 million degrees. Now, stars are very hot. Stars are not quite that hot. That is not something that could be attained by a star that is only fusing hydrogen into helium, which, in order to get any, a star might be able to get that hot if it had already like fused carbon-12 and was like fusing higher elements than that, it might be able to get that hot. But certainly before fusing carbon, or before fusing something to make carbon, no way a star's getting that hot. So
this could have been a bottleneck in the fusion process.
yeah, and exactly. And if we don't get carbon, we don't get the stuff after carbon, because that's how stars work. They keep fusing heavier and heavier elements together. And so if carbon's cut out, we have hydrogen and helium, and that's it. We don't get anything more. And so this is really problematic, because the prediction we'd make from this is, well, there shouldn't be any carbon in the universe. That's a very lousy prediction, because there's clearly carbon in the universe. So what's going on here? So a man named Fred Hoyle ended up finding the solution to this, and he found it using quantum mechanics. I don't want to get too deep here, but in a very basic way, in quantum mechanics, atoms can be in different energy states. They can be at a ground state, which is their lowest state, or they can be in excited states. That little diagram there is showing an electron going from an excited state to a less excited state. Atoms can also do this as well. It's not just the electrons. The atoms can also be in those same energy states. The ground state has low energy. The excited states have higher energy. But the important thing is they're quantized. The electron, or the atom, can only be in one certain energy level or another certain energy level, i.e., its energy could be 1 or 2 or 3 or 4, but it could never be 2.5. It could never be 3.5. It could never be 4.7. Like, these values are just impossible for them to have. They have to have a very specific energy. And so, but when an atom gets into an excited state, it knows how to like handle that energy. It can drop back down to its ground state, emit light, and it's all good. So what Hoyle found was that if there's too much leftover energy produced by the beryllium-helium collision to get carbon, the newly formed carbon just rips itself apart. So even if we get the beryllium to fuse with the helium, if there's too much energy, it just breaks the carbon back out into beryllium and helium. So we don't even get fusion to happen. It's just like they basically just bounce off each other pretty much, is what ends up happening. And so to make carbon, we need to do something with that energy. A great thing would be to just let that energy be absorbed into the carbon atom and send it to an excited state. But in order for that to be the case, that energy has to be a very specific value. It has to be the value equal to one of carbon's excited states. So in order to make carbon, we need to have an excited carbon energy level at an energy equal to the energy of the beryllium, the energy of the helium, plus the thermal energy of the star. Remember, these things are racing at each other at high speeds. We also got to take that into account. That's extra energy there. So Hoyle studied this and predicted that a carbon excited state would be at this energy. So we just basically took this like, well, in order for carbon to exist, this has to be the case. So I think it's going to be there. No one knew if it was there at that time. But eventually in 1953, William Fowler found it exactly where Hoyle said it would be. So Hoyle, under the assumption that basically this carbon energy level had to be fine-tuned in order for carbon to occur, made an accurate prediction of where that carbon was going, where that carbon energy level would be without knowing it beforehand, just under the assumption that it would have to create carbon. So the energy of carbon itself seems to be finely tuned. There's no real reason why it should be equal to beryllium plus helium plus thermal energy. That's not a thing in physics. That's not something we could have predicted. Very lastly, just a brief example, brief final example, moving out to cosmology, to like the universe as a whole. Through observation, we've determined the universe is very, very flat, which, flat on a universal scale means basically space isn't warped. It's a Euclidean geometry. Basically, if you send out parallel rays, they're always going to stay parallel. They're never going to like fly apart. They're never going to crash together. In a flat universe, they're always going to stay the same distance apart. And that seems to be the universe that we're in. The thing is, though, if the universe was a little bit more curved, it would collapse in on itself way too fast to make galaxies. And if it was negatively curved, something that's the closest example is a Pringle. Imagine what a Pringle looks like. That. If it was negatively curved, it would cause super rapid expansion, and it would just pull matter way too far apart to make fun stuff like galaxies and stars. And so this is strange about how flat the universe really is. And again, there's no specific reason for it to be that flat. It's also very smooth. And by smooth, I mean it has basically the same density everywhere, except for a very small area, or some regions that have slightly more matter than others. But the clumps of matter are only 1 in 100,000 times more dense than average. What this means is basically we have a volume over here with 100,000 galaxies in it, and then we have the same volume over here with 101,000 or 100,001 galaxies in it. Those are the kind of density difference. It's like if you're looking at that, you no way you could tell a difference. But that tiny difference does a lot for universe formation. So with it at its current value, it's great. We have this great universe that we live in. If it was 1 in a million, so if it was even less, matter wouldn't have been able to collapse properly. And again, fun stuff like galaxies and stars, they just wouldn't form. There just wouldn't be enough gravitational strength to collapse them in and make structures. If there was more clumping, if it was 1 in 10,000, stars would be packed too tightly. We would get stars, but they'd be packed very tightly. And we actually have an example of that in our current universe, the galactic core, that has a lot of stars packed very, very tightly. And back in the day, they kind of thought that the galactic core that might be a good place for life because there's a ton of material there. There's probably a ton of planet-making metals and stuff. But in reality, there's just a bunch of radiation. There's stars going supernova all the time, i.e. exploding and just sterilizing all the planets around them. And the stars are also flying past each other really close. This could fling planets out into deep space. This could make their orbits really elongated and send them really far away from their stars. So this isn't, it's not like life is impossible here. It's just much less likely, and it wouldn't seem to last very long. If it was 1 in 100, so if it's much more dense, and remember, this is just 1 in 100 still, just, 99 galaxies here, 100 galaxies here, giant black holes consume most matter. And by giant, I mean these black holes would be the size of thousands of galaxies, not stars, galaxies. So that's the kind of universe we get from just 1 in 100 difference. Imagine if it was any more clumped than that. So again, the level of smoothness in the universe, very, very fine-tuned and has very disastrous results. So as of right now, that's, all the examples I'm really going to give. There's a ton of others that from different areas of physics, but I hope you get an idea of what we're looking at when we're talking about fine-tuning. These values that they really have no real specific reason for them being very specific values, and that if we if we change them a little bit, life just shuts down. Anything resembling life just shuts down. So the rest of this talk, I really want to focus more on objections to this, because there's a lot of objections you could raise. And I want to go through them one by one. So first one, the good old puddle analogy. So who here has read Hitchhiker's Guide to the Galaxy? Indeed. So good old Douglas Adams, in addition to writing that book and teaching us what the meaning of life was, he also formatted the puddle analogy. And I will give some grace here. It seems to have been more so formatted as an argument against planetary fine-tuning, oh, why is the Earth so great for life? Which I honestly have some problems with that line of reasoning as well, but that's besides the point. The thing is, it's been applied to the universe a ton. So I feel like I need to point it out. But it basically goes, in essence, well, if a universe is super different, so what? Life, finds a way. It will adapt to just any universe you give it. Okay, sure, if we transplant one of us into these universes, we'll die, all right? If you transplanted yourself into deep space, you'd die. But surely surely in some way, some strange exotic form of life would form in these universes. And so they wouldn't really be inhospitable, just inhospitable to us, but hospitable to something else. So, I was going to play a video from YouTube to like explain his actual talk, but last time a speaker played a YouTube clip, the live stream got copyrighted struck. So, at least I thought I noticed that. So anyway, I'll just read this in my best impression. This is rather as you imagine Puddle waking up one morning and thinking, this is an interesting world I find myself in. This is an interesting hole I find myself in. It fits me rather neatly, doesn't it? In fact, it fits me staggeringly well. Must have been made to have me in it. This is such a powerful idea that as the sun rises and the sky and the air heats up, and as gradually the puddles get smaller and smaller, frantically hanging on to the notion that everything's going to be all right. Because this world was meant to have him in it, was built to have him in it. So the moment he disappears catches him rather by surprise. I think this may be something we need to be on the watch out for. So what are we really saying here? That the puddle sees this hole that looks like it was made for him, when in actuality the hole wasn't. The puddle just adapted to the hole. The puddle could have been in any hole, and he would have just formed to fit that shape, just in the same way as we're saying life in any universe could just, adapt itself to the shape of that universe. Shape of that universe, essentially. So, where this fails, and I'm sure some of you may have already seen it already, given what I was just talking about. This fails to take into account how just utterly broken the other possible universes are. Go over some symptoms of broken universe. Some I've discussed. Some of them come from other fine-tuning problems. You could have something like short-lived stars, only a few million years, and not long enough for evolution to create life to arise. And you might be able to say, okay, well, but that's not like impossible for life to occur. And like, okay, perhaps something is, maybe it's less optimal, but still possible. But then we have stuff like no carbon or oxygen, and again, maybe silicon-based life forms, but silicon is just not as optimized for life. Then we start getting into the really problematic territory. Stuff like no elements besides hydrogen. You don't get complex structures out of hydrogen. It just can't do anything. You can't get DNA out of that. You can't get anything resembling DNA. You can't get anything resembling information. It's just a gas bumping into each other. Then you go even further, you get stuff like atoms are unstable. Like that's like the neutron universe we were looking at. There's no atoms even. It's just particles bouncing around. And then furthermore, we could get universes where there's only black holes, or that it's expanding so fast that each observable universe is a single particle floating on its own in billions of light years of empty space. Like these are the kind of universes we're talking about here. These aren't just, this isn't something that, oh, well, if we try hard enough to think of some alien that's different than us, it might be able to survive there. This is stuff that just basically almost the fabric of reality as we know it is just non-existent. So another thing that's brought up is problem of normalizability, which, what does that mean? Well, it comes down to the question of like, what are we actually saying when we say something is like fine-tuned to, oh, it's fine-tuned to 1 part in a million? What does that mean? Because if these parameters are just constants, like, couldn't they be any possible value? Like, sure, we have a parameter that's like, I don't know, like 12 or something like that, but couldn't it be anywhere between like 0 and infinity? So in that case, why is 12 any less likely than any other number, or even a range? Even if we say that, oh, well, between 1 and a billion is life permitting, that's still super fine-tuned because it could go all the way up to infinity. So how do we even assign probabilities to that? If they have an infinite range, it's just not something we can really just put a number on, or is even really worth talking about. The thing is, though, they don't have an infinite range. These values are defined within a framework, and that framework is our modern-day physics understanding. The modern-day physics understanding breaks down at these things called Planck limits. It's just kind of just a limitation to our theories. And these constants only exist inside our theories. So it makes no sense to apply them where our theories just aren't really theories anymore. And so the the Planck limits, there's different dimensions of them, like different values of them. There's a minimum length, there's a maximum mass, there's a minimum time, there's a maximum temperature. There's these values like this, and of course you can combine different ones to make new units that are Planck units. And if any of these constants create a situation where we're violating one of these Planck limits, we can just throw that case out. And so this actually does give us a finite set of values we can test for, because there's the only set of values that are valid under our theories. So it makes sense to limit them here. And so, now we can actually start defining probabilities. So, but then again, what if possible universes, what does that even mean? Is that even a coherent concept? Like, maybe the universe is just the way it is. We only have a sample size of 1 after all. All I'm talking about is just random hypothetical possibilities. Like, it's just the universe. So I think a helpful exercise would be to think, is there any precedent in science for considering some other possible universe? For considering, the what-if scenarios of, well, what if the laws of physics were different? What if the constants of physics were different? What if initial conditions were different? Is there anywhere else where this could be the case? And I very much know that there is, and it is called cosmology. So we're going to take a bit of a dive into cosmology. Does anyone have any questions at the current moment? No? Oh, yeah, Alex? All I covered before fusion was quark masses. Those being different and making the proton like unstable and leading to universes with like hydrogen or neutrons, and that's it. That's all I really covered. Yeah. So the basic rundown of how modern day cosmology works is that, like a lot of the other theories, cosmology also has certain parameters that could be any possible value. And we don't really know, we don't know a priori what those values are. We need to go discover them. We need to go measure them. We need to go figure it out. And so, some of these important parameters include, these are the ones I'll at least, mostly omega m, but these are some of the most important ones, omega m, omega lambda, and h. Omega m and omega lambda are measures of density. Omega m is a measure of like the real matter in the universe. Omega lambda is a measure of the dark energy in the universe. And h is like an expansion rate, how fast the universe is expanding. And so, again, we don't really know these values just off the top of our heads. We got to go measure them. How dense is the universe? I don't know. It really could be any density. And so in order to discover what parameter values are actually out there, we point our telescopes at the sky. We measure countless amounts of data from galaxies, exploding stars, supernovas, and the cosmic microwave background radiation, the afterglow of the Big Bang. And we take our math, we look at all of our different possible parameter values, and we plug in those parameter values into the math, and we make predictions about, well, if a universe had this parameter and this parameter at these values, what would it look like? Oh, well, if one had a different value and a different value, what would that one look like? And which one is closest to what we actually observe? And so an example of this right here, this was lifted from a 1998 paper done by the High Z supernova search team. This paper ended up winning a Nobel Prize for discovering the acceleration of the expansion of the universe. But basically right here, we have a plot of the supernova luminosity, basically like how bright the supernova looks from Earth, versus its redshift. You can just think of redshift as a distance measure. Well, it's more complicated than that, but it's basically a distance. So, and these numbers are flipped basically to where bigger numbers are dimmer, lower numbers are brighter. So, as you can see, it makes sense. The further the exploding stars are away from us, the dimmer their explosions look to us. Cool. The thing is, though, if we plug in different values for omega m and omega lambda, there's slightly different paths that curve can take. And so here, even on this graph, we're considering 3 different possible universes. where these parameters are different values. And then those black dots are our actual data, like each of those is a supernova we measured. And we're looking at it and we're saying, all right, which line fits it best? And I think even on here, not so much for these, but on that top corner, I think you can even see that that solid black line lines up better with those dots than the dashed lines do. And that solid black line is one that has omega lambda in it. So we didn't know before that. We didn't know if omega lambda was 0 or not. But using this data, we realized we were in the possible universe where it wasn't 0. But it could have easily been the case otherwise. So yeah, considering a possible universe that is not our own is actually very useful, and it's pretty much what all of cosmology is based off of. Might not be said in those words in cosmology, but it's basically what it amounts to. Making predictions, making predictions based on hypothetical parameters, it's not an absurd notion, and it's not unique to fine-tuning. What I really want you to get out of this is we're not just making this up for fine-tuning because it supports our case. This is found in other areas. We're simply applying it to more than just cosmology. We're applying it to other fields of physics as well. But even if we know that we can consider other universes, what do we do about the likelihood of a possible universe occurring? So what I mean by this is, let's just think of an example real quick. Imagine you have some parameter that can be between 2 and 12 inclusive. Those are the Planck limits we were talking about. And I'm just going to restrict it to integer values so it's easy to think about. And I don't know what this parameter is. Maybe it's omega d for omega ducky. I don't know. But we know that life can only occur if the parameter is either a 6 or a 7. So you might immediately think, okay, well, there's 2 ways of getting life-permitting values out of that from 11 different possibilities. So one might just naively assume, oh, well, 2 divided by 11, that's 18.2%. Cool, that's the amount of fine-tuning we have. Not a whole lot. Obviously, in a real-world scenario, probably be way worse than that. But just as an example, that's our predicted amount of fine-tuning. But the question is, how are we generating these numbers? Because if we kind of think deeper, what if we're rolling 2 dice to generate them? And you might see now why I chose 2 to 12. So the thing is, in reality, when we're rolling 2 dice, it's a very different probability distribution. We have a ton of 7s and a ton of 6s, and not as much of the other numbers. And so when we actually do the math, we find that there's actually 11 ways to generate a life-permitting universe, where there's only 36 possibilities. 11 divided by 36 is 30.6. So this is way higher than what we just estimated. So we are overestimating the amount of fine-tuning because we didn't know how those dice were being rolled. We didn't know what was generating those numbers. And there was a hidden assumption that we were making earlier. We were making the assumption that every single value had equal probability of occurring. But that's not the case here. They have different values of occurring. But I do have to say a caveat on this. From this, a new question can end up being raised. Why did the life-permitting values line up with the highest probability rolls? If it ends up being that 2 and 3 were life-permitting instead, we'd get a likelihood. There's only 3 probabilities of that, and so 3 divided by 36, that's 8.3, and now we're underestimating fine-tuning really badly. And so, the real reason why 6 and 7 were chosen was because I, Seth, am an intelligent agent, and I devised this to make a point. But there's really no reason for them to be either way. So even making this argument, it seems to, you can make it in any case to say we're overestimating or underestimating fine-tuning. So just keep that in mind. But let's return to cosmology. The observations of the universe, they indicate that omega m is about 0.3 right now. That's just our best estimate for it. And what that means is 0.3 matches way better with our data than 0.2 or 0.4. But the thing is, what if 0.3 was actually a highly unlikely value because of some deep physics we don't know? Maybe there's some cosmic dice behind the scenes being rolled that happen to make 0.3 super, super unlikely. And in that case, it actually might be more likely that we live in a 0.2 universe but our observations are just really, really, really skewed. And sure, we have good data, scientists do good data, and they measure good things, and I don't think it would be the case that we'd mess up that badly and all of our models would be pointing in the same direction. But it could. And if the odds of a 0.3 universe existing are truly just astronomically low, it becomes more likely that we just misread the data. But then again, 0.3 could also be an extremely likely value. And then at that point, it's really, really likely that we're in a 0.3 universe, way more likely than we're even saying. And so in a way, we can kind of just think of these two possibilities as canceling out. The main point is, like, we don't know. We don't know if there's deep, unknowable physics behind the scenes that is driving the distribution of how these parameters are going to lay out. But you can either throw your hands up in the air and just say we don't know and not do anything, or you can make an assumption and try to proceed with science from there. And that is what cosmologists do. They make an assumption that every parameter has an equal probability of occurring. And so too, we're going to make that assumption here as well. Again, this is not an assumption we're just making up for fine-tuning's sake. It is being used elsewhere. If we're wrong, then the predictions and likelihoods of cosmology are also in trouble, which would be very sad for me. So a summary for the case we've laid out thus far. The constants and initial conditions of the universe are sitting at a razor's edge to allow for life, moving a little one way, moving a little other way, completely inhospitable universes. Without it, life couldn't exist. Again, it's pretty much just completely impossible for life to exist in these broken universes. Our theories allow us a way to assign probabilities to a life-permitting universe. And we can know from this that they are unimaginably low. And looking at cosmology can provide an example on whether possible universes are something to be considered. And we can assign a prior probability based on what is commonly practiced in cosmology. So that's at least the stopping point before I get in the possible explanations for all this strangeness. But I hope I've established that this stuff's pretty weird. There's something strange going on with the universe. The constants should not be these very specific values for life, and yet they are. And I think at this point, doing away with some of the initial objections that I was saying, I feel like at this point, it should be clear that this is something worth thinking about a possible solution to. So with that, does anyone have any questions?
About that uniformity assumption for like G, for example, that you started out with, do we assume that, just because I don't know the background behind this, that all possibilities of G are uniformly distributed? And I'm wondering kind of what their original thinking process behind that was, because in finance, where I'm in, we almost always make a normality assumption rather than a uniformity one. So I'm wondering if there's a
Define normality assumption.
normal
And what you mean?
Yeah.
Okay, like yeah. Centered on what?
Just centered on the rate of return that we have. Oh yeah, that's a good.
Yeah, no, but for this case, centered on what?
Yes.
The value we currently have? How do we know the value we currently have is the most likely value?
Yes. Okay. Thank you.
All right. So with that, though, we can go and attempt to, provide an explanation. And so the first explanation we're going to look at is, a very interesting one, a very mysterious one. The great and holy multiverse. Yeah. So let's go over the multiverse. And yeah.
A uniform distribution, in order not to go to zero, you need an upper bound.
I covered that a bit earlier. No. The Planck limits serve as bounds to, basically we can just have like a step function, essentially is what we'd be looking at. Yeah. Our constants only make sense in the physics that we currently have, and our physics theories break down at the Planck limit, so it doesn't make sense to say that those constants could exist there. Yeah. Alrighty. So let's think about, a solution here. So we're going to grant that the vast majority of possible universes are completely inhospitable, completely. the thing is, what if these possible universes exist? I know we've been operating on the assumption that they don't, but what if they do? What if all possible combinations of parameters exist somewhere? Somewhere in the totality of existence, they're out there. What are we going to expect from a universe like that, or from a multiverse like that? And no, I'm not, at this point, I'm not making any, scientific claims about that. That's just, if this were somehow the case, what would we expect to find? And so you might initially think, well, what's that going to do? The odds of a life-permitting universe are still astronomically low. What's adding more of them going to do? The vast, vast, vast majority of them are just going to be dead, neutron-laden wastelands. How does that help us? But it does help us due to the anthropic principle. And that's because we, i.e. life, intelligent creatures, people with rational minds that can observe the universe, we're the only ones who actually, to observe a universe, we can only observe it if we're existing in it, if we're living in it already. And so it's no wonder we find ourselves to be in a universe that could support our existence. It's the only place we could be. There could literally be just trillions of dead universes out there. And honestly, that's a pretty conservative estimate. Trillions of dead universes out there for every one life-permitting universe. And of course we're going to be in that life-permitting universe because we couldn't exist in those others. Like if you went to one of those other universes right now, let's say you go to the neutron universe, all the protons in your body are just going to convert into neutrons and you're just going to decay into dust like at the end of Infinity War. Like there's nothing to see there. You can't observe these. And so all we need from the universe is to generate one life-permitting universe. And we know that a life-permitting universe is possible. And so if a multiverse goes through all possible combinations of parameters, it's eventually going to hit the one we're in. And so in that case, it does very much help this fine-tuning problem. Yes, Alex?
Isn't this basically the puddle analogy, except there's only one place the puddle could exist?
I mean, I guess sort of. But the line I was drawing with the puddle analogy is like there being other life in other places that could be different. So I mean, technically, it's still a bunch of places where the puddle can't exist. It's just the puddle can only observe his own existence in the hole that he could exist in. But so now the thing is, is there anything from science that can produce such an arrangement such as this, as an infinite number of universes shuffling through all possible values? And sort of. Let's go through inflation. So remember what I was talking about earlier. The universe is super, super flat. It's super, super smooth, very, very strangely so. A possibility for this is going to be fine-tuning, but another possibility has been brought up as inflation. That if the universe expanded really, really fast at the beginning, like really fast, like extremely, extremely fast, like inflating from like less than an atom to like the size of a basketball in 10 to the minus 36 seconds or somewhere around there, then we could actually get a universe that's as flat as we have and as smooth as we have. And so that inflation actually would solve our problems. The thing is, though, inflation isn't really like a cause, it's an effect. This is just assuming, well, what if the universe expanded like that? Well, the immediate question is what caused the universe to expand like that? And right now, there's no agreement on that. And frankly, there's no agreement on if inflation even happened. This is still a very hotly debated topic. And so, here's our first caveat, is that it's important to note that inflation has not been proven yet. There's not a whole lot of evidence for it at the current moment. It does help our models work. And, it's still a commonly considered possibility. So it is worth considering. But it's certainly not this thing we know happened in the universe. And even more so, it's definitely not something we know what caused it. There's a lot of possibilities. Yeah?
I remember hearing that in the late 2010s, there was some preliminary data that came in that physicists thought at first proved, or at least was constituted evidence for inflation. But then when more data came in, it turned out that data was actually just a fluke.
Interesting. Yeah, it's certainly. Yeah. it's certainly still something that's being debated through and ground through. Like I see papers come up with it in my research of like, oh, what if this inflation model might work? I don't know. We see, stuff like that. So it's very much still kind of in its infancy of trying to get its footing. Pause. I'm saying that even if inflation happened, that doesn't mean we know why it happened. We can't just say, oh, inflation happened and that's that. Like, that's not an explanation. We need an explanation for inflation.
Finely tuned version of inflation.
Yeah.
It can't inflate for too long, right?
Yep. And that could be another problem. But the thing is, one of those possibilities for why inflation happened could be this, the inflationary multiverse. And this would be a large expanse of constantly inflating spacetime. Just stuff that's just flying apart, expanding faster than you could possibly imagine. And in small little regions, that expansion slows down enough to create a bubble of not that much expanding spacetime. And in these bubbles, these are basically universes. And all the other bubbles, there's inflating space in between. They go flying off so much further than you could possibly imagine, so much further than we could possibly measure, so far separated, completely unobservable, completely undetectable, and completely causally disconnected. But they would be out there. And so this could be a way, if inflation was caused by this giant inflating expanse, this could be a way for other inflation, like pockets where inflation stopped, to happen, in addition to our universe. And so from this, we actually get a free solution to fine-tuning. So if a multiverse is reality, and the one I just described, then the initial conditions of each universe would be different when they form. You have different universes collapsing in different places in different ways. That's going to kind of shake things up in them. And so when you get them to collapse, they're going to start out in different orientations and different densities and different positions and stuff like that. And so in this way, we have this generation system where we can create unlimited number of universes. If this inflation's usually taken us, inflation multiverse is usually taken as something past eternal and future eternal, which do with that assumption what you will. But in this case, it would eventually shuffle through infinite number of universes. It would eventually land on one with the correct initial conditions. And of course, due to the anthropic principle, we're bound to be in the one with the correct initial conditions. And so, boom, problem solved. We've solved fine-tuning. Except for the fact that fundamental constants exist. This does nothing to explain the fundamental constants. These are still fine-tuned, and we have no explanation. So let's throw on another hypothesis. String theory. So a possible workaround is string theory. If string theory is true, string theory basically posits that all of the fundamental particles we were talking about earlier are really just, they're not particles at all, they're just strings, little 1D things that vibrate at different frequencies, and each of those vibrations are different particles. So instead of assuming a ton of different particles, we assume one thing, a string, and it just vibrates differently. There's a ton of math that goes into this. Somehow we get multiple dimensions out from this. But all in all, string theory allows us to get a changing of the fundamental constants through the string landscape, which it predicts to contain about 10 to the 500 different possibilities. And these string landscapes would have different constants. And so basically what we're saying is a new universe gets formed. Everything kind of shakes up in it. The new initial conditions fall out from that shaking, and they're different each time. And then also through that, the string landscape is going to act like an initial condition. And so a new string landscape gets formed just as a consequence of the universe forming. And then the landscape dictates constants. And so that decides the new constants for that universe. So, okay, now we have something that could solve pretty much all of the fine-tuning we're talking about here. The huge disclaimer. String theory is extremely far from proven. Used to, it was a lot more of a theory that people were very on board with. Nowadays, I think it has really fallen out of favor. I hardly hear anything about it anymore. The very common consensus is it just kind of was a failed theory and is probably just going to be relegated to the dustbin of history. And so it used to be a candidate for the theory of everything. I've heard it referred to as the theory of nothing nowadays. I really did. I've really had someone say, like, it used to be the theory of everything, but now I guess it's just a theory of nothing. So yeah. I'm not saying string theory is impossible, but it is on very, very shaky ground. And so if we're assuming a multiverse that it needs string theory to solve what we want to solve, and it's already hypothetical with the multiverse, this is getting pretty shaky. And so let's have a list of the assumptions we just made. So first of all, the flatness and smoothness problems are legitimate and demand an explanation. I think this is a safe assumption. I think cosmology has shown that the flatness and smoothness problems are pretty legitimate, and yeah, I think they should have an explanation. So this assumption feels like good. However, then we have the assumption that inflation did occur in the distant past, and that it solves the flatness and smoothing problems. This one's, still decently reasonable, but certainly far from proven, and there's definitely alternatives. Then we have that inflation was actually caused by an internal inflationary multiverse, which is even more hypothetical. And again, this builds on this. The probability of this being true is compounding on the probability of this being true. And then to top it all off, we have string theory is correct and the string landscape exists, which I think is probably the most dubious assumption of all. So we've discussed thus far, different assumptions we're making. That's not necessarily problems with the theory. That's just, shaky ground that we're building it on. Let's actually discuss a problem now. Why is the universe so large? The universe is huge. It is massive. There are galaxies so far away. There's billions and trillions, billions of galaxies, possibly around trillion galaxies in the observable universe. Surely life on the planet that we're on right now does not need those galaxies to exist. There is a galaxy right now, I'm sure, 3 billion light years away, that maybe scientists have looked at in a telescope, maybe they haven't. If that galaxy blipped out of existence right now, I don't think that would do anything to Earth. And so, why is it all there? We could have easily have just developed and survived in a universe consisting of only the Milky Way. And that's indeed what we thought the universe was until the early 20th century. We just thought it was the Milky Way. And perhaps we could have even survived in just a group of a few stars. Now you may say, oh, well, can't we just survive around our own star? And I would say this, but I think we need other stars to produce heavy elements. Again, going back to the whole carbon is produced inside stars and stuff. We need stars before us to generate heavier elements to create stuff like planets and life. So that's why I say here, I don't know if we could cut it down to a single star. I think we need multiple stars. But still, 10,000 stars would be a blip compared to the galaxy and could probably be enough to support us. So why is the universe so big? Is this something we expect from the multiverse? The answer is no, it's not. Good old Roger Penrose there, who is Nobel laureate. He actually did a Zoom call with to UTD students several years ago because he worked with a man named Wolfgang Rindler, who was a big UTD physicist who also worked with my research advisor. So Penrose has a bit of a connection to UTD. That's beside the point. But he roughly calculated, again, rough calculation, that for every observer, so this is every person in a universe our size, there are 10 to the 10 to the 23 observers or people in a universe 10 times smaller. 10 to the 10 to the 123. That's not just a number bigger than the number of atoms in our universe. That is a number with more zeros than the number of atoms in our universe. This is unimaginably large, doesn't even actually quite seem to scratch the surface of what this number is. And even if he's wrong by quite a lot, needless to say, the multiverse has a hard time of producing larger universes. Let's just say that. And it's really absurd to think that it is at all likely to find ourselves in a universe as big as the one we're in now, when we could easily exist in a universe 10 times smaller, easily exist in a universe 100 times smaller, or 1,000 times smaller. So why isn't the universe smaller? And so you could say that a multiverse model like this would predict a smaller universe than the one we're in, and therefore that is a failed prediction of this multiverse model. So, is there a multiverse? You know, the multiverse is typically usually cited as the best like naturalistic explanation for fine-tuning. I put naturalistic in quotes because we are looking outside of our own universe at this point, which I think we kind of have to do. And it is more naturalistic in the fact that, you know, we're still thinking of physics theories and fields and stuff like that. But if we define the natural world as everything we can possibly observe and be causally connected to, multiverse is technically a supernatural theory. But you know, that's all right. The problem is that it's still extremely highly speculative. It's nigh unfalsifiable. Maybe there might be a multiverse theory that comes along one day and makes an accurate prediction about our universe that we're in. But so far, I don't think any of them are really at a point in their theories at this point to be like making those predictions, and especially not confirming them. And other than that, they just have, oh, the universes might be out there somewhere, but we can't possibly interact with them. The best models we have are riddled with problems. There are even more problems that I didn't even have time to mention. And again, they only explain the constant fine-tuning if we allow for string theory, which again, very dubious assumption. And so again, I can't sit up here and say a multiverse is 100% impossible. It could be the case, but I think it's very far from a coherent theory, or certainly not an outgrowth of our current physics knowledge. Very hypothetical. Yeah?
Are there any naturalistic physicists who have suggested some way to solve the origin problem with the multiverse? Because it's, in my understanding, it still doesn't answer the question, where did it come from?
Well, that's what I was saying. Usually the inflation multiverse is taken to be eternal.
Oh,
Just
sure.
always expanding forever into the past. Yeah. Maybe there's, you know, you point out some problems with that, but that's not as much the focus. Yeah.
I know very few philosophers or anyone who thinks about anything, not even atheists, take this idea seriously. But the idea, not even most atheistic philosophers and physicists would take this idea seriously. But there is the there is the there is the mathematical realism card that you could play and suggest that all universes are really just mathematical constructs,
Sure.
and that or just mathematical objects, and that including ours and whatever the heck other universes there are. And I know that and
That's Max Tegmark's
yeah,
theory.
That's Max Tegmark's idea.
Oh, I guess I didn't realize it was Tegmark. That interesting.
But I do actually think that that's a better that's a better multiverse hypothesis than this inflation
Okay.
stuff.
Interesting opinion. Yeah.
It's ad hoc, but at least it will
Yeah.
explain things.
Sure.
I think
So.
I think its predictions are catastrophically worse than any of these, though.
Really.
I don't think Tegmark has any appreciation for how wild the world
Well, take it from the mathematician in the room.
You would know better than any of the rest of us.
So let's move on to another possibility. Is there some sort of God? So perhaps we have a different explanation. Maybe the universe looks fine-tuned because it is. Because there was made for a certain end in mind, which really appears to be life. This is also known as the teleological argument, i.e. like made towards an end in mind. So the thing is, if we're thinking about like some being out there who fine-tuned the universe, who altered physics itself to very fine-tunedly, you know, make the constants such that life occurs, one, this being would have to have some kind of rational will, or at least some kind of desire. It has to want a certain end to happen in order to do this. It has to want life to occur. This sounds like something with a mind. This doesn't just sound like a natural process. And additionally, something that's able to alter physics itself and also comb through the Googles and Googles of possibilities of different universes and find the one that actually works. Something incredibly powerful and something incredibly intelligent. Now, of course, I have to now have another disclaimer. Like the cosmological argument, this is a very general theistic argument. We are not getting any particular religion really out of this. But this definitely, such an argument still does not bode well for naturalism. And again, I tried to cover the naturalistic explanations before this to show that they don't really hold up as much. So, I know we're over time a little bit, but is it okay if I finish this? Okay. So, okay, cool. Hopefully I'm not losing everyone. I'm going to format this argument in probably a very strange way and take it in an odd direction that you probably won't see coming. So, this topic, it's still very much in its infancy. It's very speculative. It's very just fine-tuning in general. It's pushing up against the limits of physics and human understanding, honestly. Like, it's so hard to talk about some of these things, to talk about, oh, other universes, other multiverses. It's hard to understand. It's hard to comprehend. And there's a ton of terrible, terrible maths behind it that I certainly don't even understand. But, so I can't sit up here and tell you that the universe or the multiverse physically impossible or that fine-tuning is 100% proof of God. But I don't think I need to. So I'm going to make a comparison to a very different argument than fine-tuning. The problem of evil. Bet you didn't see that one coming. I think this is actually a pretty similar argument to fine-tuning, and let me explain why. If there is it basically goes along the lines of if there is a good God, why is there evil and suffering in the world? And I'm going to lump these two into one. And my point in bringing this up is not to discuss a bunch of possibilities about solving the problem of evil or anything. I don't want any questions about what do you think about the soul-building theodicy. Like, I don't, I don't want any questions about that. This is still a fine-tuning talk. I am making a comparison. But this is still, it's a big argument. It is used a lot. It's commonly cited as one of the best arguments against God. And frankly, I agree. I think it is a pretty good argument when framed correctly. I think it can be framed incorrectly. There are two types of arguments that come out of this, a logical one and a probabilistic one. The logical one, I'd say, does not really hold up. And that is saying that it is logically impossible for God to allow evil to exist for some length of time. I don't think this holds up because there are things like theodicies that exist, fine-tuning, soul building, the law of triumph, stuff like this, that can at least provide a possible route. You may disagree, you might not think they're good enough, you may think they're unlikely, but they're at least logically coherent and logically possible. And so I don't think the problem of evil really works when framed as God absolutely can't have a world with evil. I think it works a lot better framed as a probabilistic problem. And basically putting it in logical syllogism form-ish, we can say that a universe with random, pointless suffering is more likely to arise through an uncaring atheistic universe than one that has an all-good God. The universe we observe has random, pointless suffering. It is more likely that a good God did not create our universe. And I think this has some merit to it. I think this, looking at the universe, it does have a lot of pointless suffering that does seem to be surprising under theism. And it does make more sense under an atheistic universe that has, at bottom, no design or purpose, just blind, pitiless indifference. So I feel like this works. However, we can also frame fine-tuning in basically the same way. So I present the probabilistic problem of fine-tuning, and I call it a problem because it is a problem for naturalism. A universe with constants fine-tuned for life is more likely to arise through a God-created universe than one that lacks meaning and purpose. The universe we observe has constants fine-tuned for life. It is more likely that God did create our universe. So here, we're looking at two different aspects of the universe, one that seems more likely under atheism, one that seems more likely under theism. And I personally feel like they hold, and I use this word roughly, around the same weight. You can think one's higher than the other, you can think the other is higher. I don't really care with that. I just, my point is I think they both hold enough weight to balance each other out enough to where it's not a landslide. To where just if this was the only two arguments you had to go off of, that you might come, somewhere in the middle of, okay, I could see either side. And in that case, that's really interesting. That means we are at least saying that there is a possibility that there is a God that, fine-tuned the universe for some end. So I think these are very, similar arguments. They both show a probabilistic likelihood. They both there's workarounds, there's alternative explanations, like, the free will defense or the multiverse. There's different ways around these. But on the face of it, each argument shows a fact about the universe being more probable under, atheism or theism. And so the thing is, though, I feel like the problem of evil gets a lot more weight because, frankly, it's just a lot more difficult. It has a lot of emotional strings attached. It is really hard to deal with. But I think if we're trying to look at this from a rational, logical standpoint, I think we need to admit the fact that they are very similar arguments that go in a very similar way. And so don't give the problem of evil more weight just because it has more emotional strings attached. Like, we want to separate emotion as much as possible. I know it's impossible to totally do. But we want to at least be, conscious of that. So I'll leave you with this, that there are several aspects of the universe which point to the possible influence by a god, and if that would be the case, that would be a supernatural influence. Just possible. I'm not saying it is. It's just a possibility. But I think one that is likely enough to be worth considering. And if it's at least possible that physics was supernaturally fine-tuned for life, it follows that physics could be supernaturally altered in other cases. Apparently, this being out there wanted life to occur. Perhaps he wants to communicate with this life in some way or make them know he's there in some way. And so with this, we should at least expect the possibility that there could be different supernatural influences in the past. Like, we shouldn't, I feel like this is enough to not just cut out miracles a priori, to think that we at least have some kind of reason to believe there may be more going on to this universe than we see. More going on to the natural world, that there's something outside of it causing these constants to be what they are. And if that's true, then, perhaps there is supernatural influence somewhere else in our history. And I'll just leave you with the question of, looking back through any historical events, does anything jump out at you at a place where that might have happened? Alrighty. I am finally done. Yes, Alex.
I could say that there's, you're talking about how the problem of evil can be given more weight than the problem of fine-tuning because of the emotional weight that the problem of evil has. But I could make the argument that the problem of fine-tuning could be given more weight than the problem of evil because the problem of evil is contingent on the existence of things that can be judged as good or evil.
That's honestly a fair point. Yeah, that is indeed a fair point.
Can't even say anything.
Yeah, that's true. Wait. Yeah. But the thing is, the problem of evil still works as an internal critique. That under Christianity, under any theism, there is some good and evil, and so why do we expect evil under such a moral framework? So I still think it works as an internal critique. Yeah. No.
So maybe the very thing he said he didn't want to.
Oh my gosh. Yeah.
I've heard in similar discussions talks about how the laws of physics themselves could be different as opposed to just the constants.
Mm-hmm.
Is that beneficial to think about at all, or would it run into the same issue of how do you assign probabilities to it? If there's no plain limit.
I mean, the thing is, yeah, what? It's certainly worth considering, why are the laws of physics the way they are? There are certainly also things we discover and we can't just know off the top of our heads. But yeah, how do you assign those probabilities? Where do you draw the line with that? Could it be that any possible mathematical formula could be a physics equation? If that case, we're starting to get to that form of the multiverse where any math could be a universe. So
There is something Robin Collins 20 things that are more of like binary choices of like, do like charges repel or attract? He documented a number of just kind of things like that.
Yeah.
Actually, there's a bit of a interesting selection in some of those kind of things at that level.
Yeah.
But it wasn't
And
all
there's-
possible laws or anything like that. But I think he documented about 20 of those kind of binary choices that had to be right for life.
Yeah. And there is a lot of like symmetry to the universe that like simplifies a lot of stuff down, and you know, like, I mean, it makes sense that forces are going to act in a like a central force motion kind of way to where they're spherically symmetric, even forces going out in all directions. Like, you know, you definitely can make assumptions like that. But yeah. Anyone else? Yeah.
In this analogy you people make with the arguments from evil,
Mhm.
have there been, I assume there have, but are there impressive attempts to quantify like the probability weight? I mean, it's obviously not controversial, but it's relatively straightforward, I would think, for those fine-tuning problems relative to something like, evil existing with
Yeah. Definitely much harder. I've never seen any like quantitative.
the closest,
You know.
if you're going to talk about one argument being of
Yeah.
the same strength as the other, then the first thing you'd want to know is the probability.
Mhm.
The closest I've seen to that is an argument where it's what choice do you make on what to believe. Where it's like if it's probability versus payoff. Where it's like if the probability of a God existing is so low, but the payoff of following him and being aligned with him.
Almost like a Pascal effect.
Well, the payoff
Yeah,
of
but
my
that-
God is exactly that plus one. Exactly.
Oh no, it's Pascal's mugger.
Infinity plus 1 equals infinity.
But it's higher.
But it's bigger infinity.
It's bigger.
No, he can give you an uncountable infinity.
That's the closest I've seen. It's never about quantifying like what's more likely. It's quantifying what's most beneficial for you, most likely.
But that is definitely a certain like criticism of it, that even when problem of evil is framed in a probabilistic manner, it's a qualitative sort of like look at it, but you can't really ascribe numbers to it. It's kind of just based off of feeling.
We're running a little out of time. We may
Yeah.
want to take it to the restaurant for
Okay.
another discussion, if that's okay.
You can.
I mean, if you can say that there is a correlation between goodness and preventing suffering, then if we have one set that has a good origin and one set that has a neutral origin, that correlation would seem to indicate that the set with a good origin would have less suffering, right? Or be less likely to have suffering?
Yeah. I mean, yeah. I feel like you can get like a less out of it. It's just like how much less is the problem that doesn't really have an answer. Alrighty. Are we good? Okay.